Hello everyone. So today we're going to be talking about exponential growth and decay and their graphs. And I'd really hoped to do a bit of investigating on this before you watch this video. So that we're going to look at this as an introduction to graphing, and then we're going to spend some more time in class really kind of investigating the graph. But for now, we've looked at all different types of functions, and here's some examples of functions we've looked at. We've looked at f of x equals 50x. Hopefully you see that as a line with an average rate of change, a constant rate of change. We've looked at cubic functions, kind of like blue, but that's only half the graph. It would kind of squiggle through 0, 0. We know that its shape kind of looks like that. But the big question is, and there's the line, the big question is this function right here, 2 to the x. We haven't faced any functions yet where the exponent was actually an x. We've talked about like quadratic functions and polynomial functions, but none that look like that. And if you look at the green graph, it appears that this is actually getting bigger and bigger as x gets bigger and bigger, it's growing, and then all of a sudden, so it's growing slower than the cubic function and slower than the line until it gets to right about here. Here on the line, it starts growing faster than the line, and here it takes over the cubic function, and we call that an exponential function. So what do we do when the exponent is an x? So just like I've asked you, how do you know something's quadratic? How do you know something's cubic? How do you know if something's linear? I can look at these functions and notice that the exponent is an x, and so these are called exponential functions. Again, the exponent is an x. See my play on words? And all of the numbers in each of these mean something to us, and we're going to investigate that in this lesson. But let's talk a little bit about an exponential graph. Okay, an exponential function, let me fix this a little bit. An exponential function is any function that is in the form y equals ab to the x power. So we would call that standard form, y equals ab to the x. And remember, the only way I can make that look a little funnier is to change y to f of x and use function notation. Okay, now a couple things have to be true. A has to be greater than 0. If it is 0 or if it's negative, then it's this wouldn't be an exponential function. And b has to be greater than 0. Now, it can be a fraction, but it's got to be greater than 0. B also can't be 1, okay? Because if it was the number 1, let's talk about that. We raise it to an exponent. We raise it to the 2. We raise it to the 3. We raise it to the 4. We wouldn't really need an x because 1 to any exponent is just 1. All right, so let's look at the two different ways that we can look at this graph. We can have when b is a greater than 1, so it's a number greater than 1. We call that exponential growth. Okay, what happens to the graph is that it's increasing as it gets to the y-axis. It hits the y-axis and then it grows. We call that exponentially. So exponential growth is growing along the y-axis as x is getting closer to infinity. Exponential decay is when something's falling from left to right. So it starts way up and then it gets to a point and it flattens off as it gets close and close to this number. Now, there's a couple things that we're going to want to know about the graph, okay? The exponential function, we're always going to be considering what is the y-intercept, okay? So we need to know that. And it has something that we haven't quite talked about yet. It has something called an asymptote. This is an asymptote. Now I want you to think about what I just am drawing, what you might call it, okay? So actually, the definition of an asymptote is a line that a function gets very, very close to but never crosses. So don't touch those asymptotes, okay? This graph, it's going to get really, 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 really close to it, as close as it possibly can, but it's never going to actually cross that graph. And that's called an asymptote. It also has some other key features that you're going to want to know. You're going to want to know how you'd find an additional point, okay? So we're going to need to know the general shape, whether it's growth or decay. We'll be able to find the y-intercept. We'll be able to find one additional point on the graph. And then we're really going to want the equation of the asymptote and draw it in. And then that'll lead us to the domain and the range. Okay, so let's look at y equals 2 to the x power. Remember, we've talked about domain. Domain is any value on the x-axis or any value for x that I can put into this function and make it be a defined function. Well, the two that we have issues with are when we have x in the denominator of a fraction or when we have x under the square root, because those have some domain restrictions. But this doesn't. We can put any number in for x as long as it's a real number and it will work. We'll be able to graph something. So the domain is all real numbers, which we write as negative infinity, comma infinity. Now the range, let's go back to that graph we were just looking at. The range is all the y values, and if it's getting closer and closer, it starts at that asymptote and goes all the way up, it's always going to be above the asymptote. So it will always be a horizontal line, okay, greater than whatever the equation of the asymptote is. And the equation of the asymptote will always be y equals, because it's a horizontal line. And we're going to practice, okay? That's just some general information about this graph. Okay, but here's a really good example of an exponential function in the form y equals ab to the x. Okay, so first we're going to look at b. B tells me if it's growth or decay. Okay, so b is going to tell me if it's growth or decay. And we said that if b was greater than 1, it's growth. Okay, so this is growth. Why? Because b is greater than 1. The y-intercept. Okay, so how do we find the y-intercept? Remember, the y-intercept is where x is 0. So I'm going to let x be 0. We'll get 2 to the 0, which is 1. 1 times 3 is 3. Okay, so my coordinate of my y-intercept is 0, 3. All right, my asymptote, because this is the parent graph, is that this is going to get really, really close to y equals 0. So I'm going to draw in my asymptote first. Okay, just like that. And I'll actually draw on the y-axis, just like that. So you can see the horizontal asymptote happens to be, in this case, the x-axis, okay? So there it is. All right, I'm going to plot my y-intercept of 0, 3, which is right here. Now, I am going to get 1 to 2 other points on the graph, so I'm going to plug in points. Okay, so I'm going to plug in x is -1 and 1. If x is -1, we get 3 times 2 to the -1. So there's that negative exponent. So we have 3 times 2 to the -1 means 1/2. So we get 3 over 2, which is 1.5. Okay, and then if we plug in 1, we get 3 times 2 to the 1 power, which is 2, and that'll give us 6. So I have enough to plot and graph this -1, 1.5, and 1, 6, which is going to be way up here. So I'm going to get my graph. I'm going to grow from left to right. I'm going to go through that y-intercept, and I'm going to shoot up just like that. All right, the domain. The domain, we've already said, this is not a fraction or a square root, so it would be all real numbers. We can write -infinity to infinity. The range, we always pay really close attention to the asymptote of y equals 0. And so the range would be y is greater than 0, okay? Because it's going to take on every y coordinate greater than 0. All right, let's look at another one. Is this one growth or decay? Okay, b is less than 1 but greater than 0, so it is decay. That means it's falling from left to right. It's going like that. Because b is less than 1 but greater than 0. All right, y-intercept. We let x be 0. You might be starting to see what's happening with the y-intercept. It's 3. So my y-intercept would be 0, 3. you might be starting to see that it is the a term. As long as it's just being raised to an x power and nothing else, then the y-intercept is going to be the a. But that's not always the case. Okay, the horizontal asymptote, the equation of the asymptote. This graph is not being shifted at all, so it will be y equals 0. Okay, I'm going to go ahead and draw in my axis right there. I didn't do it on the last one, so I'm going to label x and y. I'm going to put in my horizontal asymptote of y equals 0. I'm going to plot that y-intercept. I know this is a falling graph. I'm going to plug in points. I'm going to plug in -1 and 1. If I plug in -1, I get 3 times 1/2 to the -1. We have a fraction raised to a negative exponent. So guys, that's going to make it flip and become positive. So we flip it, make it positive. So that gives me 6. Where on the other side, if I plug in 1, I get 3 times 1/2 to the 1, which is 3/2 or 1.5. So you can see it's just a flip of what we just did. That's pretty cool. And let me plot those points. So -1, 6. So it's going to be way up here. And then 1, 1.5, right about here. And then I have this falling exponential graph going like that. All right, your turn. I want you to consider this function, okay? Graph the function, state that, oh, did we do domain and range? We didn't do the domain and range on the last one. Okay, so let's do the domain and range. Remember, we don't have any issues with our domain, so it would be all real numbers are allowed to be plugged into a table if we wanted to. And the range would always be, in this case, greater than the asymptote. All right, I want you to consider this one. -3 times 2 to the x. What does that do to the graph? Now, you may remember in all of our other functions, that's the a term. Now I've made the a negative. So hopefully you're seeing that that's going to reflect over the x-axis. Reflect over the x-axis. All right, so the first thing that I want to do is I want to find whether it's growth or decay, okay? Now, just because it's reflecting doesn't mean it's growth. It doesn't change that, okay? So this is growth. It's just going to look a little funny, okay? And we want to find the y-intercept. So to find the y-intercept, we're going to set x equal to 0 and solve for y. 2 to the 0 is 1. 1 times -3 gives me a y-intercept of -3, so it would be 0, -3. Okay? All right. I'm actually going to also tell you our asymptote. The asymptote here is still 0 because this graph is not shifting up or down. So there's my asymptote of y equals 0. Okay? So a verbal description of what's happening here is that this is being reflected over the y-axis. We can also say that 2 to the x is being stretched, vertically stretched, by a factor of 3. Okay? All right, so I need a couple other points on the graph, so I'm going to make a quick table. I'm going to plot that 0, -3, which is down here. You can see it's below it because it's reflecting over it. I'm going to plug in -1 and 1. All right, so -3 times 2 to the -1 gives me -3 times 1/2. So -3.5, which is -1.5. Plug in 1, I get -3 times 2 to the 1, which gives me -6. So very similar to what we were just doing. We're just doing some things to the graph. So -1, 1.5, and 1, -6 is going to be down here. 1, 2, 3, 4, 5, 6. And now this one's going to start here and go like this. Okay? All right, now we got to talk domain and range for a second. All right, so the domain, we still, even though it's negative, we have no issues with our domain. It is going to be -infinity to infinity. Okay? And the range, now you might notice this is below the asymptote, so it's going to be y's less than 0 because it's going to have y values along the y-axis below the origin. All right, guys, that's some basics on the graph. We are going to spend some time working on this in class and kind of understanding some real life examples with exponential growth and decay, which I find to be fascinating and really current and helpful. So hopefully that was something that you understand. You'll be able to apply it when we get to class tomorrow. Have a great day.